Alright, so we're going to go ahead and do one more little video here. This one is continuation. Before we talked about electric charge, now we need to talk about electric force. And you will have seen this equation a couple times, so this shouldn't be a very long video. Just want to kind of explain how to use it. But it was the Coulomb force. The electric force is the Coulomb force. You'll probably hear me refer to it as the Coulomb force. And it is, again, by this equation, K Q1 Q2 over R squared. There's another version, I believe was the original version, so this is the version that you need to know right here, but there was another version, just because I told you I'd talk about this, it was actually 1 over 4 pi epsilon naught Q1 Q2 over R squared. This is what's called the permeativity of free space. It's how strong electric fields are in a vacuum. And there's that 4 pi. 4 pi r squared, that spherical symmetry I talked about in the previous video for the electric force and the gravitational force. But there it is, 4 pi r squared. But they got sick of kind of writing this 1 over 4 pi epsilon naught, so they just, plugged it into something, did 4 pi times epsilon naught, did the reciprocal of it, and called it the Coulomb constant, just replaced it with that. So this is the version at this level that you need to know. If you get to higher levels of physics, you start using this version because this epsilon naught becomes something you have to be very familiar with. So that's Coulomb's law. That constant K, Coulomb's constant, is, and sometimes that has a little sub c, like a K sub c for Coulomb constant, is about 8.98 times 10 to the ninth. So this is actually a bigger number than the gravitational constant. Newton, we have to have a meter squared to cancel out with the r squared, and then a Coulomb squared to cancel out with the Coulomb squared we get on the top. So it's the opposite. Instead of the kilogram squared in the denominator, it's the Coulomb squared, but otherwise the same kind of units as the other. This is, of course, a vector. It's a vector, and so it acts like a vector and it adds like a vector. So if you want, say you had like 5 different charges acting on one charge, the net force on a charge is the vector sum of all the individual forces from all other charges. So what I mean by that is, say I have a positive charge sitting here, right? And then over here I've got a negative charge and another negative charge and maybe a positive charge sitting here or something. And what I would do is come through and say, all right, this is the force from the positive charge repelling it, and then over here I've got an attractive force attracting to that one, and over here, let's say that's not as big of a negative charge, so I've got a littler force here, and I'd have all these forces. And if I wanted to know the total net force acting on this positive charge, I would have to do the sum of all of them. So if I just kind of transferred over here, I've got this charge, I've got that force, this one here, then I've got, you add them up tail to tip, walkable path, I've got this force there, that's that smaller one, and then I've got this positive charge that's kind of acting up like this, and then you'd have to go through and do that to get the net resultant force, and this would be the force on that positive charge right there. You have to add all these up. Of course, depending on the number of these other charges and everything like that, this can actually become very, very difficult and very cumbersome, but technically speaking, you should be able to figure out anything that would happen with the electric force just by using this law here. This is a vector, and going through and doing this, going through and figuring all of this out, and you should be done. It might take you, a few million billion years to sit there and go through and do the calculation, but technically speaking, you should be able to figure out anything that'll happen given enough time, and just using Coulomb's law, going down and saying, all right, how much does this electron affect this proton here? So like, maybe I have like a giant, a big, spherical ball here that's charged and some square thing over here that's charged, and I could go through single charge by single charge, every single electron, every single proton, do this whole law on all of them, add up all the, the billions of trillions of charges and vectors that I'd get and go through and do it, and technically I would be done and it would work. Unfortunately, that really can't be done feasibly in anybody's lifetime or even by supercomputers or anything. They'd run for billions of years trying to do even some simple ones. So you come up with more math tricks. You get into doing things like calculus and things like that, and doing this as in bulk forces, and it kind of breaks the workload down. But it still stays pretty darn difficult because you're doing this a lot. And technically, even though we are done completely with electrostatics, we're going to come up with a few math tricks in some future videos to help kind of whittle that workload down and start making this a little simpler. Okay? So as you probably have guessed at this point, since I drew these far apart, this is definitely a field force. All right, this is a field force, which means it acts over a distance. It doesn't have to be. It doesn't have to be in contact. These charged objects don't have to be in contact. It acts over a great distance. And then here comes the part where I'll just kind of quickly tell you about how Coulomb actually made this law up. This Coulomb force here. Basically what he had was this container in it. This is just a super short version. Inside it, he had a little charged sphere sitting here, and then hanging from this little other balance was this other charged object, and it was on this kind of springy torsion thing. And so this was what was called a torsion balance. And what he could do is put different amounts of charge on this sphere as this sphere, and it would either attract and rotate this sphere toward that one or repel it and push it away. And then by measuring how far it was either twisted or rotated, he could figure out how much force this sphere was applying to this sphere, and he was able to work out this Coulomb's law up here, this inverse squared law that we now named after him, from using this object like this. So this would just rotate one way or the other by twisting it, and it took a certain amount of force to twist it like that. Okay? Just be kind of familiar with that basic idea, and you should be good. Okay? I think that's pretty much it, other than, of course, doing some practice problems trying to add up the forces of these things. And yes, unfortunate, it is a force, which means you have to do all these vectors, which probably takes you back to breaking these into components and then taking the components and making one big right triangle out of it and trying to add up and find what that is. It's kind of a pain, but again, ultimately, you should be able to do anything with it. We're essentially done with electrostatics, with the exception of trying to work out some easier ways to do these problems, and that will be in future videos. All right, that's all.